All right, let's dive right into this. If you're working in industrial piping, you already know that as the scale goes up, your engineering choices become exponentially more critical. Today, we're zoning in on one massive piece of the puzzle. What exactly is an ASME B16.47 Series A flange? In this explainer, we're going to break down the core engineering decisions to answer what an ASME B16.47A flange actually is in practice, and look at the legacy standards and dimensional rules that dictate how we handle really large diameter piping.
Here's our blueprint for today. We'll start by looking at what happens beyond standard pipe sizes, define the Series A heavyweight, compare it directly to Series B, and then dive into matching yield strengths. After that, we'll run through some actual torque specs and wrap up with how to avoid some insanely costly procurement errors.
So let's establish the core problem right off the bat. If you've been working with ASME B16.5, you're perfectly fine. Well, until your pipe hits 24 inches in diameter. But what happens when your project outgrows that? The dimensions in B16.5 simply don't extend past 24 inches because, honestly, the committee never designed them to. That leaves a massive gap for major infrastructure. Things like cross-country pipelines, petrochemical plants, and large-scale power generation facilities.
Enter ASME B16.47. This is the standard specifically built to take over right where B16.5 leaves off. It covers large diameter steel weld neck and blind flanges from 26 inches all the way up to a massive 60 inches, handling pressure classes 75 through 900. Now, the materials generally align perfectly with B16.5, with the exception of nickel alloys, so your pressure temperature tables will still look largely familiar. But here's the catch. Once you step into B1647 territory, you're forced to make a choice between two very distinct categories, Series A or Series B.
Okay, Section 1. Beyond standard pipe sizes, leaving B16.5 behind. We really need to understand that choosing between Series A and Series B is not just a matter of preference, because mixing them up can lead to some disastrous and highly expensive installation failures.
You see, B16.47 isn't merely a continuation of B16.5. It actually represents two entirely different engineering philosophies that developed independently before they were finally unified under one single code. So when you're specifying a large diameter flange for, say, a process plant or a massive water infrastructure project, you're stepping into a standard that strictly divides the world into two camps.
Moving on to Section 2, the Series A heavyweight built for external loads. Let's really focus our attention on the primary subject of our explainer today.
Now, what's genuinely fascinating here is the legacy lineage. Series A flanges trace their roots directly back to MSS SP-44. That's a standard developed by the Manufacturers Standardization Society. So if you ever spot MSS SP-44 flanges on a blueprint, you are looking at an ASME B16.47 Series A flange. Dimensionally, they are the exact same thing. They're built significantly thicker and heavier, featuring a larger outside diameter, and they rely on fewer but much larger bolts. Because of this robust, incredibly heavy-duty build, Series A is absolutely the undisputed industry standard for severe applications. We're talking about new oil and gas transmission pipelines or extreme high-pressure, high-temperature process piping. Those massive bolts and thicker flanges aren't just there for show. They're designed to handle not only internal pressure but severe external loads. Think about bending moments, extreme thermal stress, and the sheer, brutal physical weight of large-bore pipe hanging off a compressor inlet. Plus, if your project calls for a ring-type joint and RTJ facing, Series A gives you the coverage you need all the way from Class 300 up to 900. This brings us to Section 3, Series A versus Series B. The heavyweight versus the lean flyweight. Because honestly, the best way to truly grasp the engineering behind Series A is to compare it directly against its counterpart. Think of Series A as the heavyweight champion and Series B as the lean flyweight. While Series A comes from that MSS SP-44 standard we just talked about, Series B traces its lineage to API 605. Series B is much more compact, it's dimensionally lighter, and uses a tighter bolt circle packed with more smaller bolts. Now, Series B is fantastic for internal pressure and creating a really stiff joint to prevent gasket creep, which makes it popular in replacement work. But, and this is absolutely critical, they are not interchangeable. You literally cannot mate a Series A flange to a Series B flange. The bolt holes simply will not line up. No way around it. And this brilliantly illustrates the contrast. When you break down the features, you immediately notice how Series A has that larger outside diameter and fully supports RTJ faces, which Series B doesn't cover at all. Conversely, Series B offers a Class 75 pressure rating. That's super popular for lower pressure or vacuum applications where weight is a primary concern, but Series A doesn't offer that rating. So the typical use cases are entirely different here. You've got Series A for high-load new construction and Series B for leaner, internal pressure-focused retrofits.
Moving into Section 4, matching yield strengths and decoding the ASTM A694 system. Because when Series A flanges are used in cross-country transmission lines, we have to look really closely at the steel's chemistry.
On transmission pipeline bids, your Series A flanges won't just broadly say carbon steel. They're going to reference ASTM A694. This spec covers forgings for high-yield pipeline service. The grade designation, things like F42, F52, F60, or F70, tells you the specified minimum yield strength in KSI. The entire point of this system is matching. If you have an A694 F60 flange, it's explicitly engineered to be welded onto API 5LX60 line pipe. You can't just shrug and guess here. Welding a lower yield flange onto a higher yield pipe requires a carefully engineered transition, otherwise you're asking for trouble.
Let's see how these requirements stack up when you encounter genuinely harsh environments. The standard SP-44 or Series A rules, those are just the base layer. If you're in hydrogen service, you've got to overlay ASME B16.5 rules for hardness. Moving sour gas, NACE MR0175 mandates strict hardness limits, generally maxing out at 187 HBW for A694. And if you're building a B31.4 pipeline in the freezing Alaskan cold, you'll need supplemental Sharpie impact testing, often marked as S5, performed at the minimum design temperature. These are critical, non-negotiable layers engineered right on top with the base dimensional spec.
Let's get into the math with Section 5, Torques and Technical Specs, by the numbers. Let's look at the actual, real-world data piping engineers interact with every single day. Take a look at these bolt torque values from UIP International for a Series A Class 150 flat flange. Notice the scale we're talking about here. A 26-inch pipe size requires 24 individual bolts, and each one is 1.25 inches in diameter. Jump up to a 60-inch flange, and you're dealing with a massive 52 bolts at 1.75 inches each. I mean, you practically need a crane just to torque the thing down. The data also cleanly splits the minimum and preferred torques based on whether your elastomeric gasket is below or above a 70 Jurameter Shore A hardness rating. That is the exact level of precision required for large diameter joint integrity.
Now, it's also worth pointing out how these specs interact with other industries. This check bulletin from Garlock highlights the overlap between ASME and AWW water infrastructure standards. Sometimes dimensions overlap beautifully, but other times, an incorrectly sized gasket meant for an AWW flange might actually protrude right into the inner diameter of a B16.47 flange, causing process intrusion. Proper dimension matching across standards is absolutely vital. Finally, Section 6, selecting the right flange and avoiding costly errors. Let's wrap this up by looking at exactly where procurement usually goes wrong. So, the absolute most crucial point to remember is that large diameter flanges are high-dollar items, and mistakes here will completely blow up your project budget. First off, never assume F60 is a pressure class. It's a material yield grade. Second, while Series A and SP-44 share dimensions, they don't share material certs. An A105 carbon steel flange might meet Series A dimensions, sure, but it is not a high-yield SP-44 flange. Third, don't forget your bolting. Standard B7 bolts will fail in sour service. You absolutely must upgrade to B7M. And finally, always ensure your material test reports include the full chemistry and Sharpie data when required. Which brings us to a final, pretty important question for you. Are you 100% sure your current large diameter spec perfectly matches your line pipe's yield class and external load requirements? ASME B16.47 Series A is a remarkable piece of engineering standardization. It's designed to handle the heaviest, most demanding piping conditions on Earth, but its effectiveness relies entirely on the precision of the engineer specifying it. So double-check those blueprints, talk to your piping engineer, and ensure you've got the heavyweight champion working correctly for your system. Thanks for joining me on this explainer, and we'll see you next time.